Welcome to this video. My name is Giancarlo Calderon. I'm a student of aeronautical engineering, and in the next video I'm just going to explain an essay that is coming from Digital University by Andrea Morales. The name of the essay is Application of Higher Order Euler Method in the deflection of homogeneous beams. So the essay starts with explaining how the beams work. So we have this beam from A to B. We have the symmetric axis in the middle, and this is going to be our point of reference, so we can make the axis in G, in Y, and the axis in X. We have some forces being applied to the beam here, and what this chart explains is that we have these forces being applied, so the beam is going to be deflected, and we're going to have a deflection value that is going to be taken from the symmetrical axis at the beginning, and the here it would be till here, to the symmetrical axis at the end when the forces are being applied. This Y is what we really want to get from the problem. We just want to verify what is the maximum value that, depending on the forces that we have, what is the maximum value that beam is going to be deflected. So this is what we want to verify from the problem. So this problem takes in base this draft that we have here, that is a beam from A to B. This beam from A to B is being held in both extremes by a wall, so it's being supported in both extremes. We're going to have the maximum deflection angle Y in the half of the length of the phi. This is the value that we want to get from the problem, so we can know how the beam is going to be, what is the maximum resistance of the beam. So we have here that each support is carrying the half of the weight of the beam, so that is the reason why we denote this line, this vector, with W per length divided 2 and W per length divided 2. So the weight of the beam divided 2, because each support is carrying the half of the weight. And also we have some pointed forces in the beam here. These forces that we're applying here are creating a momentum in the beam that we need to know the value of this momentum, so we can know what is going to be this deflection angle that we're going to have here. We need to remember that a momentum is equal to the force being applied per the distance in a certain point of reference that we're going to have here, B. This is going to be our point of reference from which we're going to get the distances from, so we can get the value of the momentum. So given that, we're just going to find the value of all of the momentums that we have in the left side after the point B. So we just want to verify the momentums in this part of the draft. So we have that momentum X, it's equal to the first force that is being applied here. We have the first force being applied is this one, because it's the weight of the beam, and the total value from here to here. That is the force being applied to this beam. So we just replace here, and the distance where the force is being applied taken as reference B. So we know that the distance from in which the force is being applied is the half from P to here, is the half of all of this length that we have here. So it would be L minus X divided 2. That is the distance where the force is being applied, taken as reference the point P. So we just replace here, and this is the first momentum that is being applied in this force. Then we have the other force in this part. In this part, well, this momentum first is positive, because it's creating a momentum that it's going in this direction. This force is creating a momentum that is going in this direction. This one, since it's being applied upwards, is going to create a momentum that is being applied in this direction. This momentum is negative for convenience, so we put the minus sign for the next momentum that we're gonna have from this force, and we have that the force, it's the half of the weight of the beam, so we just need to replace here. This is the force being applied in that part, and now we need to get to know the distance where this force is being applied. Well, the distance where the force is being applied is from, if taken as reference P, is from here to here, so that would be this distance, L minus X. So at the end we get this equation. This equation is denoting the momentums that are being created by these forces, these two forces, just in this side of the beam. And remember that all of this is just to get the deflection of the in here. That is what we really want to get from the problem. Welcome to this video. My name is Giancarlo Calderon. I'm a student of aeronautical engineering. And in the next video, I'm just going to explain an essay that is coming from this Italian university by Andrea Morales. The name of the essay is Application of Higher Order of the Euler Method in the Deflection of Homogeneous Beams. So we know from the previous problem that we have that the momentum is equal to a w x squared divided 2 minus w per the length per x divided 2. So this is a differential equation of second order. So we just replace the differential equation for x derivative depending on the square here. So we have w divided 2 per the double derivative of x minus w per L divided 2 per x. It's equal to 0. So this is the equation that we're going to resolve, so we can know what is the deflection, the maximum deflection of the beam, depending on the forces that we're applying on the beam. So we have first we need to replace that the double derivative of x is equal to y2, the function of y2 in w, and x is equal to y1. So we need to replace these variables in this equation. So when we do that, we get two different equations. The first one is the first equation we get is that so we have that the first equation is the y1 evaluated in w is equal to y2 evaluated in w, and the second equation we have is the y2 evaluated in w is equal to w divided 2 per the function of y2 evaluated in w minus w per the length divided 2 multiplied by y1. So we have these two equations that we're going to resolve. So based on these two equations, we can resolve the Euler method. So for the Euler method, we have this equation. So we have that the value of y in the next coordinate is going to be the value of y in the previous coordinate plus the step multiplied by the function evaluated in the previous coordinates that we had in x and y. So with this equation we can predict what is going to be the value of y in the next coordinate, just based on the previous coordinates that we had before. So we have in this equation the Euler method, that we have that y in the next coordinate is going to be the result of y in the previous coordinate plus the step multiplied by the function evaluated in the previous coordinates that we had. And as I mentioned before, we're going to use these two equations that we have here, that y1 evaluated in w is equal to y2 evaluated in w, and that this y2 evaluated in w is equal to y divided 2, and y2 evaluated in w minus w per the length divided 2 per y1. So as we see in these two equations, first we need to resolve these equations so we can know the value of y2, and with the value of y2 we can know what is the value of y1. y1 is going to tell us what is the deflection of the beam, so this is our purpose, this is our main aim, and this is what we really want to get to know. So we just start replacing for this first equation with the values that we have. We have some initial conditions given by the system. The initial conditions are when w is equal to 0, y1 evaluated in 0 is equal to 1, and y2 evaluated in 0 is equal to 1 as well. So these are going to be our initial conditions. So we can predict, we can foresee what are going to be the values of y1 and y2 in the next coordinates. So we start from this formula. So y2 in 0.1, that is the next coordinate, is going to be equal to y2 in the previous coordinate. So we have that is equal to 1 plus the step. The step is going to be 0.1. So plus the step multiplied by this function evaluated in these previous coordinates that we have. So we have here 0.1 divided to y2 is equal to 1 in 0. We have here 0.1 per the length, that is 4. We're going to take the length as a constant value of 4 divided to per multiplied by 1, since y1 evaluated in 0 is equal to 1. When we resolve all these numbers and calculations, we know that y2 when w is equal to 0.1 is equal to 1. Now that we know the value of these of y2 when w is equal to 0.1, we can resolve the first equation. So we have that y1 when w is equal to 0.1 is equal to the previous y1 that we have, that for the initial conditions we know is 1, plus the step again, that is 0.1, multiplied by this function that we have here, evaluated in the previous coordinates that we had. So we have the g2, we already know that g2 is equal to 1, so we just replace for 1. And when we resolve this equation, we know that y1 is equal to 1.1. So we already know these two conditions. Now we know the value of y2 and y1 in the next coordinate, that is going to be these two numbers. So it would be 1.1. These are going to be our new first initial conditions. So y1 when 0.1 is equal to 1.1, and y2 in 0.1 is equal to 1. These are going to be our new initial conditions, so we can do the process again with the Euler method, and we can have now the values for y1 when w is equal to 0.2, and y2 when w is equal to 0.2. And you will just repeat the process all over again, so we can predict the values of each coordinate of y in the next coordinate.